In this notebook, we're going to look at the idea of definitions and some assumptions. We're going to let G be a group, and we're going to let little a be any element of G. A conjugate of A is any element of the form G inverse A times G. And let's write that just a little bit clearer. And it's worth noting that this guy, of course, has to belong to the group G. So that's all a conjugate is it's you take an element and you multiply it by some element G on the other side by G inverse. It is worth noting that if I look at A and I have a G and I have a G inverse here, and I look at G inverse A and G, these are both conjugates. Because in both cases, what I've done is I have multiplied the element of A by an element and its inverse on each side. So it's important to know that we're not really going to distinguish between the meaning of conjugate for each one of these things. It is, however, worth noting that in general, G inverse A G and G A G inverse are not the same element. So in general, they're not the same thing. So the idea of a conjugate element is not actually that bad. The interesting thing is that we can generalize this to a conjugate subset. S be any subset of G, and we are going to talk about non-empty sets. Then we have a conjugate set of S is any set of the form. Let's look at a G and then S and then G inverse. And this would be the set of everything that looks like a G inverse little s times G, where little s is all of the elements of S. And it's pretty clear that depending upon what elements are in S, this guy is not necessarily going to be a subset of S. In fact, if we just look at standard subsets of G, it's not completely clear exactly what's going on most of the time. But it does turn out that we have one really important idea. But before we go into an idea, let's just look at the idea that I want to look at is what happens if my subset is a subgroup. So what happens if we form the conjugate subset for a subgroup H of G? Well, let's actually look at an example. So let's take a basic little example. Let's let H be the subgroup generated by the permutation 1 goes to 3 goes to 4, living inside of S4. And H itself consists of the permutation that's generating the subgroup, the square of that, and then when you cube that particular permutation, you just get the do-nothing permutation, which we're writing as E. And this is a cyclic subgroup, so I'm going to remind yourselves that this is a subgroup. I actually have the wrong notation up there. That should also be. And let's just let alpha be, let's let it be a 4 cycle. 1, 2, 3, 4. Basic 4 cycle. That's clearly an element of S. And what I want to do is I want to look at, first do alpha, then do the subgroup H, and then do alpha inverse. And also first do alpha inverse, then do H, and then do alpha. And I would like you to stop the video right now. And once you have the video stopped, find these two conjugate subgroups. Actually, find these two conjugate subsets. And then restart the video. Now, hopefully you stopped the video and you figured these two conjugate subsets out. The first one looks like this. So the first one is this, and we get these 3 permutations by simply doing these 3 permutation multiplications. And one interesting where this permutation, you get this one, and if you multiply these two together, you get E. In other words, this is the cyclic subgroup generated by the permutation 1, 3, 4. And let's see, let's get that idea written in something that's not going to go away. This is the cyclic subgroup generated by the permutation 1 goes to 3 goes to 4. Similarly, if you look at this other conjugate subgroup, we realize that if we take this permutation and square it, we get that one. And the product of these two just happens to be E because the order of that permutation is equal to 3. And so this particular conjugate subset turns out to be the cyclic group generated by the permutation 1, 2, 3. And this, of course, brings up the question, is the conjugate subset for a subgroup always a subgroup itself? And in order to answer that question, we basically have to do a little bit of review about subgroups. So I want to review the subgroup criterion theorem back from chapter 3. And the subgroup criterion theorem says that we have the following. If we take a non-empty subset of a group, and we have the following, well, let's actually word this as, let's let that guy be a subgroup. Then we can state S is a full-fledged subgroup of G if and only if, which means it goes both ways, for every pair of elements inside the subset S, we have this funny-looking product, A times B inverse, belongs to S. And the backwards direction of this implication gives us an easy way to verify when a subset is a full-fledged subgroup. So what we're now going to do is we're going to look at this subgroup criterion theorem and we're going to apply it to a conjugate subset. So we're going to let S be the subset G inverse HG, where H is known to be a subgroup of G. And the question is S itself a subgroup of G? Well, we start this particular thing by picking two elements of S. So we let A and B both be elements of that group criterion. We want to know, is A, B an element of S? Because if the answer is yes, then we know that S is a subgroup. And if the answer is no, then we know that S is not a subgroup. And so that's how come we call this the subgroup criterion theorem. Well, let's see. This statement here says there exists somebody inside the set H that I'm going to call H1 such that A is equal to G inverse H1G. And there exists an H2 inside H such that B is equal to G inverse H2 times G. So now the question is we want to look at A times B inverse. If A times B inverse winds up being inside S, then S is indeed going to be a subgroup of G. If we can't show this, then we can't say that S is a subgroup. So we're going to look at A times B inverse. Now, A, remember, is G inverse H1G. B is G inverse H2G, and that implies that B inverse is the inverse of G inverse H2G, so it's that guy's inverse, and we have to reverse the order and slap the inverses on. So we're going to get G inverse H2 inverse times G inverse's inverse. And of course, G inverse's inverse is just G inverse. So we have G inverse times H2 inverse times G. That's what B inverse is. Well, once we have that, we can now compute A times B inverse. A times B inverse is G inverse H1G, and B inverse is G inverse H2 inverse times G, and we can throw those parentheses away and rewrite this as G inverse times H1 times G inverse times H2 inverse times G. Of course, this is just an E, so this simplifies down to G inverse times H1 times H2 inverse times G. And it's important to realize that this product is in H because H is a subgroup and H1 and H2 are in elements of H. And so we want to make that note. H is a subgroup, so H1 and H2 inside H are indeed going to imply that the product H1, H2 inverse is equal to something inside of H. And so what that says is that AB inverse now is G inverse times H3 times G, and that really has to be an element of S, which is G inverse times H times G. And that lets us conclude that conjugate subsets are indeed going to be subgroups of the original group when H itself is a subgroup of G. And we call this particular guy a conjugate subgroup of H. Now, the last thing that I want to do is I want to state something really important and very basic about what happens in abelian groups. So, in an abelian group, let's see, I misspelled that. So, in an abelian group, it turns out that if we have H is a subgroup of an abelian group G, then every conjugate subgroup is just going to wind up being the original subgroup itself. And the proof here is real easy. So the proof here is very straightforward. For each H inside H, we have G inverse H times G is equal to G inverse GH, because G is abelian, and that's equal to EH, which is equal to H. And so that's actually going to say that X is inside of this conjugate subgroup if and only if X itself is inside of H. Because what we can start with is X is inside this subgroup says X is equal to one of these guys. So it's important to realize that in the abelian case, conjugate subgroups are not very interesting.